Oh.
Okay.
Hello. Can you hear me? Can you hear me? Can you hear me?
Hi, I can hear you.
All right.
You're able to hear me?
Yes.
Okay, so I've prepared the whiteboard in advance this time so that I don't have to spend time writing it out, all the questions and the answers. I'm going to
All
go
right.
through you remember this question probably, right?
Yeah, I do.
Okay, we rushed through it last time, so we'll try to do this in a bit more detail. I'm going to go through it quickly once, and then after that, then maybe we can go through it more slowly with you doing some of the work.
All right.
So I'm going to go through it quickly once. Okay, so what minimum tension must your cable be able to support without having your sign come crashing down? So we're asking for the minimum tension in this cable. The second question is, what minimum vertical force must the hinge, that's here, what minimum vertical force must the hinge be able to support without pulling out of the wall? Okay, so first thing, Page 2. Here I've drawn the same diagram, but a lot larger and a lot more detailed. Okay, we have the length they gave us over here, that's 1.6 meters. We have the mass of this beam. That mass has a gravity of mg, gravitational force of mg coming from the center of mass of the beam. That's 17 kilograms. And then we have, of course, the tension, which I've drawn in gray. That's what we want to look for. That's what we want the magnitude of. And then we have two forces pulling down, two tension forces, T1 and T2, because of these two ropes or wires that they gave us in this question. So that's the diagram in more detail. And now if we were to try to get the T1 and T2, because they didn't give us that in the question, we can obtain that by looking at the free body diagram of the sine. The free body diagram of the sine has a gravitational force, capital Mg, that's 33 kilograms. And of course, this sine is not accelerating and it's not rotating. So the sum of the torques and the sum of the forces has to equal 0. So if the sum of the forces equals 0, that means T1 plus T2 equals mg, right? So T1 plus T2 equals mg.
Right.
And then we also know that the sum of the torques is equal to 0. And they told us that these are equally spaced from the middle of the sine. So T1 and T2 are equally spaced from the middle of the sine. That means their distance away from, if we choose the axis of rotation to be the center of this sine, the T1 and T2 are the same distance away from this, the axis of rotation. So T1 has to equal T2. If T1 equals T2, then we have 2T1 equals mg. That means T1 equals mg over 2. Or T2 equals mg over 2. So that's how we get the magnitude of T1 and T2. Doesn't matter the height of the sine. All we need is T1 and T2, and those come directly from mg. So next, we want to make sure that the sum of all torques around the pivot point P is equal to 0. That's because the system is in equilibrium. We want it to be in equilibrium. We want there not to be any rotation. So the sum of the torques around any point has to be 0. So let's do the sum of the torques around P. We have the torque due to tension 1, the torque due to the mass of this beam, which is mg. We have the torque due to the second tension, T2, and then the torque due to the tension that we want to find, which is this gray tension vector there. So T1, the torque due to T1, that's just going to be my distance L minus my distance S to get this distance between P and T1. So that's L minus S times the force T1. And that's in the negative direction because it's a negative torque in this case, because I've chosen counterclockwise to be my positive, my positive convention. And so I'm pulling down with a force T1 on this beam. I'm pulling down with a force of T1. That's going to cause that beam to rotate clockwise, which is the opposite of my positive convention. So I have negative L minus S T1. Then I have the torque due to gravity of the beam. The force is mg, and the distance away from the fulcrum is L over 2. The force is again in the same direction, so I have negative L over 2 mg. Then same thing for T2. The distance away from the fulcrum is capital L. It's negative because it's again pointing downwards. And this time it's not so easy to, so that's just L times T2. And then this time for the capital T, this tension vector that we're looking for, that one's not as easy because it's not a perpendicular force to the line between the pivot point and the force. The force is not exactly perpendicular to that line drawn between P and the origin of the force. So we're going to have to do the cross product of the distance from the pivot point to the force, that's L, and then the force itself, which is in this case T. So, oops, I'm going way ahead of myself there. So I think the last slide I did was slide 5. So let's do slide 6. So here now I'm just plugging in T1 equals mg over 2, T2 equals mg over 2. So I'm just plugging those in. And then to get the cross product L cross T, I suppose it wouldn't hurt for me to write this as the absolute value of the cross product, because I'm not writing T1 and mg and T2 as vectors in this case. I'm just saying that the sum of the magnitudes of the torque equals 0. So here I just need the magnitude of the cross product of L cross T. And an easy way to do that in this case is to just get, I have the force, the tension force here. I draw a line of action that's a line through the tension force. And then I find what is the distance between the point P and that line of action by drawing a line with a right angle, a line perpendicular to the line of action. I get this moment arm. That's the moment arm, the length of the moment arm. I've denoted it here as R perpendicular. That is the length of a line between P and the line of action, which is the line going through the force vector, such that the line between P and the line of action is perpendicular. The moment arm line is perpendicular to the line of action.
Yeah.
So I have R perpendicular times T, and then I just need to find R perpendicular, right? So to get R perpendicular, it's just taking some time to load the next slide. So I should be on page 7 now. There we go. So R perpendicular, I have this length here that was capital L. I said at the beginning, this is capital L. So I have L sine theta, because if that angle is theta and this hypotenuse is capital L, then this right there, that will be, well, opposite over hypotenuse is equal to sine of theta. So I have R perpendicular is just L sine theta. It's the length across from or opposite to the angle theta. And then we also know they didn't give us theta in this problem. They didn't give us theta, but we do know that cos theta equals this line, this adjacent distance, capital L, divided by this hypotenuse, lowercase d. So cos of theta equals L over d. So R perpendicular equals L times sine of theta, but they didn't give us theta. So we have to write theta as the cos inverse of L over d. So now we have all our ingredients. We have the sum of the torques is 0. That's negative L minus S times mg over 2. I've multiplied both sides by 2 here. So the 2 is gone from the denominator here. The 2 is gone from the denominator here. The 2 is gone from the denominator here. And then I just have 2 times R perpendicular times T. And R perpendicular times T, we determined that R perpendicular was L times sine of cos inverse of L over D. So that's how we got 2 times L times sine of cos inverse of L over D times T. So then we just solve for T. We put all these negative terms onto one side. We have the mg term, the lowercase mg term, the capital mg times L term. Then we divide it by the coefficient of T. So we get this, and we can simplify a little bit further by factoring out the g and just, I don't even know if I collected some like terms. I had capital L, capital mg twice. So I have 2lm there. So that's basically my formula for the tension now. That's the formula for the tension. And when we plug it into Wolfram alpha, for example, we just plug in the numbers 9.81 for G and all the numbers given to us in the question. We get 460.504 something something. And because they gave us only 3 significant digits in the question, we would report this as 461 newtons in the end. So that's part A, where they wanted the tension force in that cable. Now for part B, they wanted the vertical force at the hinge, the force in the y direction at the hinge. So to get that, we're just going to sum up all of the forces in the y direction, and the net force in the y direction has to be 0 if this is an equilibrium. And the only forces in the y direction are Fy, which is the vertical component of this force at the hinge. So that's Fy. And then we have the vertical component of the tension. So that's T sine theta, but theta is cos inverse of L over D. They never gave us theta. They didn't give us the number of degrees. They only gave us this length and this length. And then we have actually 3 vertical forces going down, but 2 of those vertical forces are mg over 2, so capital Mg over 2. So we have 2 of those, so we just have negative capital Mg over, we have negative capital Mg over 2 minus capital Mg over 2. Since we have it twice, we just lose the denominator of 2. Then we have mg, which is the force due to gravity on the center of mass of the beam. So those are all the vertical forces. We sum up so that all of them are equal to, the sum of all of them is equal to 0. We're looking for Fy, the vertical component of the force vector in the y direction. So here we go. We have we know that this net force has to be 0. We isolate for Fy, and we plug in the tension formula that we got there. This is why it's good to keep things symbolically rather than plugging numbers in right away, because by keeping this symbolic, I can actually get a very neat formula for Fy. I just sub in T, the sine of cos inverse of L over D. I have that in the numerator and in the denominator from the T, so those cancel out. And I don't have to worry about this sine of cos inverse of L over D anymore. And then I just have this nice, cute little formula here at the end, where I only have to plug in a couple of numbers into the calculator and do an addition and a multiplication and a division. Much simpler than trying to do it where I've plugged in the numbers at the beginning and then I have to type in G times this plus this minus G times this times this times this minus this times this plus this times this. By doing it symbolically, I end up with this nice formula where I can just plug in the numbers and get a very accurate answer at the end. So plugging in all the numbers from the question, canceling out all the units, I get newtons. I get 174.4340625 newtons. That's the exact numerical answer to this number of digits. And with 3 significant digits, I end up with just 174 newtons.
All right.
So that's the overview of how to do this question. Was there any part of this that's that you think is a bit confusing or went too fast?
Go back to when you found tension.
Excellent. Okay, good question. So so here I've drawn the tension in this diagram.
Yeah.
Now you want to know finding the tension T1 and T2 or the capital T here?
Well, so I just got to read what was given again. Okay, so yeah, just I would say tension in the long cable, not the sine cables. Yeah, I'm still a bit confused on that part.
So finding the tension in this big cable over there?
Yeah.
All right. Good question. Very good question. Okay. So to get that tension, we're going to say that the sum of all torques is equal to 0. The sum of all torques around this axis of rotation P is equal to 0.
All right.
So I'm going to add up all possible torques. Now there's a torque, well, there's a force at the hinge. In order for the system to be in equilibrium, there has to be some force at the hinge pushing pushing outwards like this on the beam, for example. But that force is a distance of 0 meters away from the axis of rotation that we've chosen. So we're not going to include that force. So we have torques due to 4 different forces. There is a torque. So there's torques due to these 2 wires that are holding the sign. Okay, there's two wires holding the sign. So T1 and T2, those are the tensions in those wires.
Yeah.
Those tensions are a force that has to be taken into account because they're gonna apply a torque to the system. Then you have the beam here, this orange. It's orange in the original diagram and it's orange in my diagram.
All right.
From the center of mass of that beam, there's going to be a gravitational force downwards, mg.
All right.
And then there's also the tension in the cable, T.
And do we just ignore the mass, the weight of the sign because it's not directly attached, and we could just say the tensions or what counts here?
Yeah, so the mass of the sign, that's not applying any direct force on the system here, on this system that I've drawn here. The tension that we're looking for is all the way over here, and the sign is some distance away. Really, all this tension is over here. We want to get that tension, and that tension. So at the same spot as that tension, you also have a tension due to a wire. You also have a tension due to a wire here, and those tensions are going to depend on this mass of the sign, but the mass of the sign doesn't directly. The mass of the sign, you could, if you wanted to. You could just say this is mg over 2, mg over 2. It's like the mass of the sign is evenly distributed between both wires. So you put half of the mass applying this torque and half of the mass applying that torque. But really, a more systematic approach to solving this problem is to first draw the free body diagram of the sign that has a gravitational force going downwards, which is capital Mg. And then there's 2 tensions from the wires. That's T1 and T2, both going upwards. And then in this diagram, the free body diagram of the beam, we have those same 2 tensions going downwards. The sum of all tensions in the wire is equal to 0. So we have a tension downwards and a tension upwards. Does that make sense?
All right. Okay. So I see in blue that T1 plus T2 equals mg. Is that what you're referring to on how we deal with this?
Okay, yeah, so this free body diagram right here, that's the free body diagram for the sign. Yeah. And there's a mass of capital Mg going downwards, and this sign is in equilibrium. So all of the vertical forces, which are the 2 tension forces, have to completely cancel out the downward force, which is the gravity.
All right.
So that's why T1 plus T2 equals Mg. Now, do you know why T1 equals T2?
Well, because it has to be in equilibrium.
Okay, but I already said that the sum of the forces is equal to 0 to get T1 plus T2 equals Mg. Why do these 2 tensions have to be equal to each other?
Because they're of equal distance from from the center of mass of the sign.
Yeah. So if we were to do the sum of the torques around the center of mass of the sign, we would have this force, the torque due to this force a certain distance away from the sign, and the torque due to this force a certain distance away from the sign. And because those 2 forces are going to apply torques. They're going to both apply torques to the sign, but in opposite directions. One of them is going to cause clockwise rotation, and one of them is going to cause a counterclockwise rotation. So because, and then the only other thing in the formula, you have the distance and the force. The distance, the force, and the angle. Because it's symmetric, the angles are the same. The force, the distances away from the center of mass are also the same. So then the forces have to be the same, because the only three things that go into the torque formula are distance, force, and angle. So if the angles are the same due to the symmetry, and the forces are the distances away from the center of mass are the same due to symmetry, then the forces also have to be the same.
Right.
Mm-hmm. We could have worked that out by doing the sum of the torques around the center of mass of the sign, and then figuring out what the torque, because they gave us the dimensions of the sign and stuff. So we could have actually worked out the cross product of the distance between this tension and the center of mass and the tension itself, and the cross product of the distance between this tension and the center of mass and its tension, and worked out those cross products, and calculated the torques due to each force, and come up with some relation between T1 and T2 in order for the sum of the torques to be equal, and you'll find that T1 equals T2. But here I'm just using the principle of symmetry to skip writing down the sum of the torques.
Right.
That's completely fair. In fact, you'd probably, if you just wrote down T1 equals capital MG over 2 and T2 equals capital MG over 2 directly, you wouldn't lose marks. You're not always required to do that, but drawing this diagram is helpful because it tells us a little bit more about why those two torques are equal and why they add up to the capital MG.
All right.
Okay, so you understand why T1 equals T2 equals MG over 2?
Yep.
Okay, now for the four torques, we want to do the sum of all torques. So the first torque is T1. Now, T1 is how far away from the pivot point P?
T1. Let me see the diagram. Well, T1 would be 1.6 meters minus 0.9, or L minus S.
Precisely. So I have the distance here, and then you understand why it's a negative torque?
It's negative. Wait, and we're talking about pivot point P.
Exactly.
Because that's clockwise.
That would pull the beam clockwise, correct?
Yes.
And then the force is just T1. Now, the torque due to mg, how far away is the beam from the pivot point P?
Wait, from how far is? Sorry, I didn't hear you. How far is what?
I said, how far away is the beam from the pivot point P?
You mean the center of mass of the beam?
Precisely. Yeah, it was a bit of a trick question because basically we're doing the torque due to the beam, but we know from last chapter that basically we can treat that entire extended body, which is the beam, we can treat that as just a particle at the center of mass. So instead of treating this as some long beam, we can just consider this as, we can just pretend that this long beam is a particle with no size, a distance away from the origin equal to the center of mass. The center of mass is a location.
All right.
Does that make sense? We're taking this beam and we're just pretending that it's a particle that is L by 2 away from P.
All right.
And that entire beam, so that particle basically has the same mass as the entire beam, and its location is at the center of mass of the beam.
Yeah, so it's yeah, it's L over 2. All right.
So that's the distance, and then your force is of course mg, and that's again a negative torque. Then how far away is the second tension vector from the pivot point P?
Just L away.
Capital L. So capital L times force, which is T2. Now the last force we have is this tension vector, and we have to express it as a cross product. I will actually again, I will for clarity, I will just write down. Oops. I'll express this as an absolute value because I haven't used vector notation on these forces. So I'll that's the absolute value of the cross product, because we're just doing the magnitudes of the torques, and their directions are denoted by these positive and negative signs. Now we know that this tension vector, what way is it going to pull the beam?
You mean from of tension 2?
No, capital T without any subscript.
Okay, so it would. Are you talking about how it will affect the torque? Is it?
How it would in the absence of other forces, how would that force T rotate the beam?
Okay, it will be counterclockwise.
Which is positive according to the convention we made there.
Yes.
So we have positive L cross T.
Yes.
Okay. Okay, so do you know how to calculate L cross T?
Yeah, so that would be L times T sine theta.
Magnitude of L times magnitude
Yeah.
of T times sine of theta. And theta is the angle between what and what?
It'll be the angle from the force, which in this case is tension, from the distance away from the pivot point.
Okay, so the angle between the vector L and the vector T.
Yeah.
Mm-hmm. Okay, now do you know that angle?
Well, wouldn't it just be the angle in this triangle, or oh wait, actually no. It would be how should I put this? If you move the tension
Yeah.
to the point P,
Okay.
the angle between that's the angle we're looking for. It's a bit hard to explain.
I understand what you're saying. Yeah.
Yeah.
So yeah, you want the angle. So you're thinking of moving. You're thinking of moving either the vector, either the L vector, so that its origin starts over here where the force vector starts, or thinking of moving the force vector so that its origin is where the pivot point P is.
Yeah.
So, and in either of those cases, you will get the same angle. But then, how big is that angle? Do you have enough information to get that angle?
Well, we kind of do, because we have the length from point P to the second to T2, as well as the length of the actual coil. So we have we could do arctan here within this triangle, and then using that we could find the rest of the rest of the angle.
Okay, now arctan involves
Oh wait, not tan.
opposite and
Oh,
adjacent.
arccos.
Arc cos. Okay, yeah. So arc cos of the angle equals capital L divided by D.
Yeah.
Okay, so the angle is arc cos of capital L over D. That's correct. Yeah,
So we have the angle within this triangle now.
correct.
And then to get the rest, we could do pi minus that angle.
Pi minus that angle. Okay.
Yeah, and that should give us the angle we need.
And then you know that sine of pi minus an angle equals sine of the angle
Yeah, that's true.
by symmetry. So you end up with sine of the angle, and the angle is arc cos of L over D.
Yeah.
So you have sine of arc cos of L over D. Okay, that's correct. That's correct, and that's what I got. Let's get back to the next page. So not sure how long it takes to switch pages. Okay, here we go. Still taking long, because here I just subbed in T1 equals mg over 2 and T2 equals mg over 2. Let's see, page 7. So here I got that. So the cross product, I will write again, just to make this a bit more clear. I'll write absolute value of L cross T. Absolute value of L cross T is just going to be L times sine of cos inverse of L over D times T. Now there's another way to get that that cross product, and it's using this moment arm method. Are you familiar with that?
I'm still not too familiar. Maybe we could go over that soon.
Yeah, let's go over it now. So let's go over this. So this tension force, we want the torque due to that tension force. So we want this distance vector cross the tension vector. Distance cross force, right?
Yeah.
Okay, so one way to calculate that is to draw the force vector as we have, and then draw a line that is through that force vector. So that every vector has a direction and a length. So no matter what the length of this vector is, you just draw a line through that vector. So the vector has a direction, it's pointing in some direction, and you just draw a line through it, right?
All right.
That line is called the line of action.
Line of action. Okay.
That's the line of action. And now we take the pivot point. We're calculating the torque centered around P. So we take this pivot point and we draw something called the moment arm, which is a line that goes from P perpendicular to the line of action. It's a line that is perpendicular to the line of action. It's a line going through P, the pivot point, and perpendicular to the line of action. Does that make sense?
Yeah.
So R perpendicular in this case is my moment arm. That's the line perpendicular to the line of action and starting at P. Now, instead of trying to work out the angle, and you end up doing the same thing as you do with a cross product, but instead of saying magnitude of L times magnitude of T times sine of the angle between them, we just say that this cross product is the moment arm times the force T, the magnitude of the force T. The length of the moment arm times the magnitude of the force T.
I see.
And if we want to get the length of this moment arm, then that just ends up being, if we have the hypotenuse of this triangle, we have a right angle triangle. This is the hypotenuse, right? Because this is what's across the right angle.
Yeah.
So, and then we have this angle theta here. So if I want, so this is the hypotenuse. So hypotenuse times sine of the angle here will give me the length of the moment arm, which is the length of the triangle opposite to the angle theta. So our perpendicular, the length of the moment arm, is equal to L sine theta.
I see.
Okay, so it's L sine theta. That's the length of the moment arm. So we have our perpendicular equals L sine theta. We also know what you discovered, which was that cos of theta equals L over D. It's that the length of the beam divided by the length of the cable, adjacent over hypotenuse. That's a different triangle. And so theta equals arc cos of L divided by D. And if I plug that theta value back into sine of theta here, then I get that the moment arm has a length of L sine arc cos of L over D.
All right.
Now you can see that I would have got the same thing if I did L times T times the sine of the angle between them, because L is your distance vector, T is your force vector, and then the sine of the angle between them is just sine of cos inverse of L over D. So whether you do just tension times the length of the moment arm, or if you do length of the position vector times the size of the tension force vector times the sine of the angle between them, you end up getting the same thing. Because in order to calculate the length of the moment arm, we had to do the sine of some angle anyway.
I see.
And it happens to be that we get the same thing, whether we use the moment arm method or the magnitude of R cross F equals magnitude of R times magnitude of F times sine of the angle between them. So sometimes it's easier to use the moment arm, sometimes it's easier to find the angle. You might have remembered in some of the cases it was really hard to find the angle.
Yeah.
But it was really easy to find the moment arm. In fact, you're going to see in a moment, in the next question I'm going to do, there's one where there's one force vector for which the moment arm is almost trivial. It's like you can just, it's given to you. Like, what if they gave you this distance in the question? Then they've given you the moment arm right there, and they've also given you the force vector t. Then you just multiply them. You don't even have to worry about the angle between them because you have the moment arm. So sometimes when the moment arm is really obvious or easy to get, or it's given to you, then you can skip doing the cross product and it can save you a lot of time.
All right. So are we going to the next question then?
Okay, so the rest of this you understand? So isolating for t and then isolating for t and then plugging it in?
Yep.
And the next part of this question you understand? That's the one where we want to find the vertical force at the hinge. So the hinge is exerting a force and we want to find the vertical component of that force.
Yeah.
Okay. Okay, so you understand everything about this, what I did here?
Yeah.
Okay,
Yeah, makes
excellent.
sense.
Excellent. So let's go on to another question here. Again, I'll just go through it really quickly once, and while you're listening to me, you can decide which parts of it you might want to spend more time on. Okay, so here's the question. This is a person standing on a ladder. I've drawn out a diagram that's a little bit bigger, which contains some angles here. So we have the friction between the ladder and the ground, and that is related to this normal force at the ground. There's also a normal force between the wall and the ladder. The ladder's resting on the wall, and for every action, there's an equal and opposite reaction. So the wall is going to react. The ladder is resting on the wall, so it's exerting a force on the wall, and so the wall reacts by exerting a normal force back on the ladder. And then we have a gravitational force for the ladder, and instead of drawing an infinite number of gravitational force vectors or trillions of 10 to the 23 gravitational force for every molecule in this ladder, we're just going to say the billions or trillions or 10 to the 23 molecules in this ladder are all just acting as one particle, just one dimensionless particle at the center of mass of the ladder. And then, so that particle, which is representing the whole ladder, that has a mass of m2, which is the mass of the whole ladder, and it has a position of L/2 if this is the origin, and counting this way, measuring this way, that center of mass is going to be L/2, okay? And so, and the gravitational force will just be m2g. Then you have the person standing over here. The person is standing a distance d from the bottom. So this person standing there also has a mass of m1, and so we have a force vector of m1g. We have an angle theta here. I'm not sure if they gave us well, they gave us the angle theta, so that's good. We know that the angle is theta. And I think I've described every length and every force in this and every angle in this diagram. So I'll get on to the next slide. So here we want to do, we want to start by coming up with a formula for the normal force N2, because we're going to need that for calculating the sum of the torques and everything. So we have the normal force is going to be due to two things. We have the mass of the person and the mass of the ladder. Both of those masses are pressing down on the ground here. The person is located here, but that person is still exerting a force of m1g on the ground, and it just happens that this is the location where the normal force is. And so the normal force ends up being m1g plus m2g, or g times m1 times m1 plus m2. Now, we're going to do the sum of the torques at the wall. Okay, so the ladder is resting on the wall over here, and then that can act as a pivot point. I mean, if there was too much gravitational force, then this would this ladder might fall. It might rotate downwards. That would be quite. It might rotate upwards. Well, it will rotate maybe around the center of mass axis. Maybe this part would come down and this part would come up. But basically it would fall. So this angle would become 0. And as that happens, yeah, actually, I don't think this part would come up. It would just be this part of the ladder would be coming down. And so we can calculate the sum of the torques around anywhere we want. We could calculate the sum of the torques around here, the center of mass, if we wanted to. But in the question, they gave us the hint to calculate the sum of the torques at the wall. So that's what we'll do. And so at the wall, there's no torque due to this normal force because that's a distance of 0 away from the pivot point P.
Yep.
We have a torque due to the ladder, due to the gravitational force pulling on the center of mass of the ladder. We have a torque due to the mass of the human. We have a torque due to friction, and we have a torque due to the normal force at the ground. So now how do we calculate all of these different torques? So one way to calculate the torque, which is going to be useful for both this M2G and M1G, those are both going downwards. Those are both downwards forces where the position vector between the pivot point and the force, that's going to be going in this direction along the ladder. So you have an R vector along the ladder and you have an F vector going downwards. The angle between them is pi by 2 minus theta, where theta was given to us. And so we can calculate the torque by the formula that we're used to, R cross F magnitude equals magnitude of R times magnitude of F times sine of the angle between them, which is in this case pi by 2 minus theta. And sine of pi by 2 minus theta is equal to cos of theta. So that means we have the torque right here. It's RF cos theta. And then we can just, for M2G and M1G, we can just plug in the distance for R and the force M2G or M1G for F, and then we're done. So that's how we get those those torques. Then we have the torque for the normal force N2. Now here I would rather use the moment arm method. You know why? Because I have the force going upwards. That's N2. That's the force. And then the position vector, it starts all the way here. Or I could draw it starting from the force vector if I wanted to, but it's easier for me to conceptualize this as going from the pivot point to the force. So I have this R vector here, and I have theta here. And by the Z pattern, I have that this is also equal to theta. And the moment arm is just the length of a line between the pivot point and the line of action. So the line of action is just a line going through the force. I have these dotted lines to denote the line of action. And then drawing a line that's perpendicular to that line of action and going through the point P is quite easy in this case. It's just parallel to that line right there. And I know that angle because I know this angle and I know the Z pattern. So whatever this hypotenuse length is, which is in this case the length of the ladder, whatever that hypotenuse length is, that length times cos of theta gives me the moment arm. And then I don't have to worry about doing the sine of the angle between R and F, which would probably involve moving R so that the origin of R is at the same place as the origin of F. So moving that vector over there and then trying to figure out this angle, maybe by doing 180 minus this angle and 180 minus that angle. You know, there's a lot more, it seems a bit more laborious to calculate the torque using the cross product formula here. So instead, I'm just going to use the moment arm method. R, which is the length of the hypotenuse, times cos theta, times the magnitude of this force vector F. Okay. Then we have also a force due to friction. And again, I think the moment arm method, it's even easier here. I mean, here the moment arm method is so easy because I have the friction force going to the left. I have the position vector starting at the pivot point and going towards that friction force. I could move that vector over here and then, you know, draw a bigger diagram and try to figure out what the angle is and all that. Or I can just draw a line through the friction force. That's called the line of action. And then I have my perpendicular moment arm right here. It's so easy to get that moment arm. It's just sine theta. Well, r is the length of the hypotenuse, so r sine theta times the magnitude of F. And I have my torque due to the friction here. Okay, so the moment arm was actually useful for this one and that one. We could have calculated them all using this RF sine theta thing, but on the exam you don't have as much time, so we're not going to do it that way. So then we have one more force here. What's that last force we have there? We have M1G, M2G, N2, and F. So we have one more force, which is N1, the normal force N1.
Yeah.
So here we have N1, and how can we calculate this? Okay, this actually this torque is just 0, isn't it? That's pretty easy, isn't it? Yeah, that torque is just easily just equal to 0. So my force is in that direction. Yeah, I don't even know how, I don't even need to draw this. It's just the force has a distance of 0. So we can do it using R cross F. R cross F equals R magnitude of R times magnitude of F times the sine of the angle between them. I don't even know if it's sine theta in this case. It is sine, well, I don't even know what the angle is, but sine of alpha, I'll just say. But because the distance vector has a length of 0, then this whole thing is going to be 0 no matter what. Even if sine of alpha is somewhere between -1 and 1. It's not infinity. It's somewhere between -1 and 1. So I'm multiplying a number between -1 and 1 by 0. No matter what it is, I will get 0 at the end. Even if sine of alpha is equal to 0, no matter what it is between -1 and +1, this thing will be 0. So now I can write down. The total, the net torque equation. So I have mass M1, that is a distance of. Oops, that's totally wrong, isn't it? That's mass M2 that should be that. Yeah, so let me erase that. So
all right. Mass
M1 is a distance L minus D away from the pivot point. And yeah, good. So this is M2. That's the center of mass of the ladder. That's in the center of the ladder. That's going to be L by 2 away from the pivot point.
I have a question. So you have pivot point at point P, right?
Yeah.
Did you choose that, or does it have to be there? Did the question say where the pivot point
the question gave us a hint saying to calculate the sum of the torques at the wall.
All right.
So we could have done the sum of the torques here at this part of the wall, but that doesn't help us. It helps us to do the sum of the torques at the wall here. That
will
allows
cancel
us to
out.
completely ignore the normal force N1.
Yeah, if you choose it at a point where we know the distances away from all the forces and it's on a force, then it will be a lot easier to do.
That's a good way to choose the axis of rotation, or the pivot point. So I have 2 of the forces there already. Now I want this torque due to friction. How do I do that? So the torque due to friction, friction is going to cause this ladder to move counterclockwise or clockwise.
Which force?
The friction. Friction
of that force.
That's going to cause it to go clockwise, right?
Yeah, so negative.
That's a negative. And the distance, well, okay, I already did it here. So it's going to be L sine theta times the force, which is the friction force F. Okay, and
it's 9 o'clock.
Oops. We have now, get rid of this. rid of that. Okay, excellent. Now we have, next we have, all right, we have one more force, that's the N2. So we have a torque due to that. That's going to cause it to go counterclockwise. So we have positive. And then the distance away from the fulcrum, that's going to be L. And the we already decided that we can calculate the torque using the moment arm for N2 because it's an upwards force. So it's going to be the hypotenuse, which is capital L, times cos theta, times the force, which is N2. We can leave it as N2 for now. We know N2 is equal to G times M1 plus M2. So that's what I have here. N2 L cos theta minus FL sine theta minus these two terms we calculated early on. And the question is asking us for the coefficient of friction, right? So let's calculate the coefficient of friction. So to do that, first, perhaps I don't like this denominator of 2. So I would like to, I also don't like that F is not isolated yet. So perhaps I will isolate F. Let's multiply everything by 2 and then isolate for F, or we can do both at the same time. So we'll do F equals, we're multiplying everything by 2 here. So we have negative L M2 G cos theta. Oops, that's positive because I'm moving it to the, no, that is negative. Yeah, because I'm moving L to the other, I'm moving F to the other side. So I have negative L M2 G cos theta minus L minus 2 times that, because I'm multiplying everything by 2 to get rid of this denominator. So I have 2 times L minus D times M1 G cos theta. And this is, we'll leave that term for now. And then we have, this is going on to the other side. So here, no, this is staying on the same side because I put F on the other side. So this is staying on the same side. Here we have L cos theta and 2. And then I'm going to divide this by the coefficient of F over here. And the coefficient of F, I've put F on the other side already. So the coefficient of F will just be positive L sine theta. So that is my force due to friction. Now I'm going to duplicate this page. So now I have page 8. And I'm going to remove all of this because we don't need that anymore. We already calculated all of this stuff. Delete. Okay. Oops, I deleted a bit too much. I wanted to keep this vector, the force vector. So I'm going to do I'm going to delete these. Oh, that's a bit too much, isn't it? Just delete these. And then delete these more carefully. Excellent. Okay, great. So now we have, we would like to perhaps simplify this a little bit. We have cos theta, cos theta, cos theta at the top. So we're just going to have, we can factor out the cos theta. How about that? Oh, I also forgot I had multiplied everything by 2, didn't I? So I multiplied both sides by 2. So I had 2 there, 2 there. I have 2 there and 2 there.
And you did that to cancel that L over 2?
Exactly. Well, to get rid of the denominator here, I
Yeah.
multiplied this one by 2, this one by 2, this one by 2. So I have 2, 2, and 2. And then this one was also multiplied by 2, but that just gets rid of the denominator. So next I will factor out the cos of theta. I think that's a good thing to do, because then I have cos of theta divided by sine of theta times, then I have minus L M2G minus 2L M1G plus 2D M1G plus 2L N2. Okay, so, okay, now I could also substitute N2 equals GM1 plus M2. That might be smart. So I'll have now 2L over here. Okay. I could just say that N2 equals GM1 plus M2. So that way I can also factor out a G. That would be nice. And you know cosine of theta divided by sine of theta?
Cos over sine is just tan. Oh, wait, no, sine. Yeah, sine over cos is tan. So cos over sine is cotangent.
So I have now G cotangent of theta. And not everything has a capital L. This one doesn't have a capital L in it. So I cannot factor out a capital L and then cancel it out with this L at the bottom. I'm stuck with it. So how about I write down, I have, okay, well, I have 2 capital L M1 plus 2 capital L M2 minus capital L M2. So these, so these two are going to combine into just capital L M2. That becomes just capital L M2. And then I have, so I have this one, then I have minus 2L M1, and that will cancel out with this one. Let me maybe use a different color. So these two will cancel out with each other. And then, okay, I have next, okay, 1, 2, 3, 4. 1, 2, 3, 4, 5. I have one more term, which is 2DM1. And that's not going to cancel out with anything because it doesn't even have a capital L in there. So let's divide this by 2L. Okay, so we get G cotangent of theta over 2L times LM2 plus 2DM1. That is the force due to friction. Ouch, that keeps happening. So M2L plus 2M1D all over 2 times capital L. Now, if we want the coefficient of friction, we remember that F equals mu K times the normal force. And in this case, it's the normal force at position 2.
All right.
Okay, so now we have basically that this whole thing equals, so mu K equals F divided by N2, which is equal to this thing right there divided by N2. So we have G, cotangent of theta divided by 2L times N2, which is just GN1 plus, oh, m1 plus m2. m1 plus m2. We immediately see this cancels out with that. Very good. And then at the top, we can put lm2 plus 2dm1. So that's our final answer for the coefficient of friction. Coefficient of friction just equals cotangent of theta times lm2 plus 2dm1, all divided by 2 capital L m1 plus m2. That's the coefficient of friction. Then for part B, this was an interesting question. They said that suppose that, let's go back to the question. Actually, okay, I don't even have part B written over here. Let me see if I can get it from somewhere. I have part B. Part B was a very interesting one. Not there. Okay, suppose that the actual coefficient of friction is 1.5 times as large as the value of this minimum coefficient of friction that we calculated. What we calculated there was the minimum coefficient of friction.
All right.
We calculated the minimum coefficient of static friction required between the ladder and the ground so that the ladder doesn't slip. So you need at least that coefficient of friction that I found there, because if it was any less than that, then your normal force would be bigger than your, or let's see, one of the forces would be too big. Yeah, this, the sum of all the other forces would be too big and the ladder would slip because there's not enough friction. There's so much gravity and other forces. There's the normal force over here, there's gravitational forces going downwards, and all of those things would basically cause the ladder to slip. But because the coefficient of friction is big enough to create a force F that counteracts all that other stuff, then the coefficient of friction was big enough. Now, if the actual coefficient of friction was 1.5 times as large as mu min, the minimum coefficient of friction, then under these circumstances, what is the magnitude of the force of friction F that the floor applies to the ladder?
Okay, so I guess what you could do is so 1.5 times is basically 3/2. So maybe we could multiply the coefficient we found by 3/2, something like that to start.
All right. Okay. So the new coefficient of friction is equal to 3/2 times the one we calculated just now. Oops, I didn't mean to do that. So that's how big the new coefficient of friction is. The actual coefficient of friction is 1.5 times as large as the value we just calculated. Under these circumstances, what is the magnitude of the force of friction F that the floor applies to the ladder?
Okay, so we need to find friction.
Mm-hmm.
Well, I guess up here at the top, we have friction is equal to mu k times the normal force.
Yeah.
So we could sub in mu k with 3/2 mu k, which is the friction we're looking for.
Mm-hmm. Now we could do that, except that the hint that we were given was that even if the coefficient of friction is larger than it needs to be, it's only the minimum coefficient of friction that actually ends up being applied. So this frictional force is not going to end up being stronger than all the other forces. So nothing moves. Static friction doesn't cause an object to accelerate on its own. Do you know what I mean?
I'm a bit confused.
So basically, the coefficient of friction, the minimum coefficient of friction you need is equal to this thing that we calculated. So that's the minimum coefficient of friction you need. If you don't have that much, then your frictional force isn't large enough. There's not enough friction between the ladder and the ground, and so these gravitational forces and other forces will just cause it to collapse. But once you have the minimum frictional force necessary to maintain equilibrium, the actual friction experienced will not be bigger than the minimum needed. What that means is that if you're standing on the ground, friction isn't going to move you backwards. Static friction is not going to move you backwards if you're just standing there. If you're standing there in equilibrium with the ground, equilibrium with respect to the ground, static friction is not going to move you backwards, is it?
Yeah, because it's static friction. It's not, yeah.
So the frictional force is just enough to balance all the other forces. Like so if you start moving forward, if you start sliding your socks on the ground to move forward, there will be friction going backwards, but it's only going to be enough to equilibrate the forward force. It's not going to be more than that. It's not going to actually move you backwards. It's going to slow down your movement forward. It's going to apply a force in the opposite direction to your forward motion, but it's not going to, the friction, even if the coefficient of friction of the ground was 1 billion, well, okay, it's going to be 0.999 or something. But even if the coefficient of friction of the ground was very large, if you're moving forward, the friction isn't going to move you backwards. It's just going to reduce your forward movement. Does that make sense?
Right.
Yeah, let me draw it here. So you're moving forward. Friction is balancing it. So either maybe friction is so strong that you can't even move forward. That means you're in equilibrium. There's some minimum amount of coefficient of friction you would need for that. Or the friction is a little bit smaller than the minimum required for equilibrium, and you actually do accelerate forward, but there's a backwards force counteracting that. Now, if the coefficient of friction is 3/2 times as large as it is in this case, that's necessary for equilibrium, and you're only propelling yourself with that much forward in the right direction, is friction going to be this big?
Well, if it's in equilibrium, it can't be, right? Wait, so I didn't quite catch what you said.
All right, so I'm saying, so this is the standard scenario where you're propelling yourself forward and friction acts in the opposite direction to slow you down or to restrict your forward motion, right?
Yeah.
That's the standard case, right?
Right.
If the coefficient of friction between the ground and you is larger, if it's large enough, that coefficient of friction might be so big that no matter how much you propel yourself forward, the coefficient of friction stops you from moving. So your net force is 0, and you end up with 0 acceleration. You just end up standing there. So if you had Velcro shoes on a carpet that was complete Velcro, then you'd be just stuck there. You can't, even though you're pushing with force, trying to go forward, the friction is just completely balancing that so that you're in equilibrium.
All right.
Now imagine that your coefficient of friction is 3/2 times as big as it was here.
Right.
So your coefficient of friction is really, they have super glue on the carpet, and your socks have super glue, and you're just stuck to the carpet. Is the friction going to move you backwards?
No,
So
because
the friction force is never going to be more than the other forces.
right.
I mean, it's not going to be more than the force that it's acting against, right?
Yeah.
So the minimum force that is required for equilibrium is also the maximum force that friction is going to apply. Friction does not apply more than the minimum required force to keep you in equilibrium. So it keeps you in equilibrium, but it doesn't apply more force than that. So even though the coefficient of friction is larger than it used to be, your force is still going to be the same. Force equals mu k times n2, same as before. Because friction cannot be larger than required. Friction doesn't just randomly take people out of equilibrium. It only acts to suppress forces that are trying to take you out of equilibrium. If you're in equilibrium, then friction will not take you out of equilibrium. If you're standing on the carpet, friction is not going to take away, it's not going to disturb your equilibrium.
Yeah.
Does that make sense?
Yeah, that makes sense.
Okay. All right, so for this question, everything, I guess, makes sense?
Yes.
Okay, let's do another one. Okay, let's get, I'm gonna click on, I'm gonna get the new board. Create a new room and board. Excellent. Okay, here we go. All right, another question. Let's do this. Okay. Let me get the question out. Okay, that one we have done. Oh, yeah, this is a good one. Here's a good one. Okay. I just have to copy and paste it into this board because it's in a different browser. Okay, very good. This question was a good one.
Okay.
Oops. Just taking the screenshot. Okay, and then I have to do, okay, I have to get, yeah, this is still a new whiteboard for me, so I'm still learning all that techniques. So I have to paste, and then I get this. So I get this URL for the image, which I put over here. I click image, and then I enter the URL for the image. And there we go. Okay, so here's the next question. A bar suspended by two vertical strings. Okay, let me find, I also did the solution to this, so I just have to find that in a moment. I think that was question 13. Yes, it was. So 13A, all right. A rigid uniform horizontal bar of mass M1 and length L is supported by two identical masses of strings. Oh, sorry, massless strings. Both strings are vertical. Those are the two strings. String A is attached D less than L by 2 away from the left of the bar and is connected to the ceiling. String B is attached to the left end of the bar and is connected to the floor. A small block of mass M2 is supported against gravity by the bar at a distance x from the left end of the bar, as shown in the figure. Throughout this problem, positive torque is that which spins an object counterclockwise. Use g for the magnitude of the acceleration due to gravity. All right, so question 1, we want to get the tension at the tension due to string A, the tension at string A. Does that make sense?
Yeah.
Okay, so, and we want to express it in terms of only G, L, M1, 2, sorry, G, L, M1, M2, and D. So, okay, let's make a bigger version of this. Okay. Should I draw my own diagram? Yeah, that might be better because then I can label the tensions and all that. If I don't do that, then it's too big. I mean, it's too small. Okay, so, what's going on? Oh, I see what happened. Okay. Okay, so that's my horizontal bar. I have, of course, a tension. I have, oh, that's ugly. I have TA, it's a vector, and then I have TB, that's a vector, TA and TB, and then I have a mass, M1, that's going to have a gravitational force downwards. Oh, it's really ugly. Okay, and then I have a mass, this is M1G, and then I have a mass M2 over there. So I'll draw this one at the end. Oh, that's not at the end. That's a distance. Oh, you know what? This isn't even a mass. Okay, so I'm getting a bit ahead of myself here. This is the force due to gravity at the center of gravity of the horizontal bar. So I think the only other force we have here is due to this box. And that box is a distance x away, not a distance L away. So let's put it here. M2G. Okay, now we want to do the sum of all torques. So the thing is, we don't know the, we want to get TA in terms of M1G, M2, L, X, and D. So we don't want TB to be in the formula for TA. The only way to eliminate TB is to do the sum of the torques around point B, this point right here. That way we eliminate this TB and it doesn't enter our formula, because the question wants us to get TA in terms of all variables except for TB. So we don't know TB in terms of all the other variables, then we're going to eliminate TB from the equation by doing the sum of the torques around the leftmost part of the bar. So I'll start over here. Okay, so sum of the torques around this point right here. Let's call that our pivot point. Or I'll just call this B, because then I can call this one A. So the sum of the torques around B, so we don't have any torque coming from that tension TA. We do have a torque coming from TA, of course. We do have a torque due to gravity on the bar, and then we do have a torque due to gravity on the box. Okay, and they already told us that counterclockwise is positive. So torque due to A, is that going to be a positive or negative torque?
That would be a positive.
Positive, okay, good. And what's the distance between point B and point A?
D.
D. And how much is the force at position A?
Tension A.
TA. Okay, and then we have a positive or negative torque from the two gravities, from the two.
They're both negative.
And how far away is this one from the pivot point B?
That would be L over 2.
L over 2. Okay, and the magnitude of the force, that's easy for you to do, right? And similar for the other one, how far away is this one?
That one is X away.
X, M2G. Excellent. And the sum is 0. And the question asked us to get to isolate for TA. So TA equals, I can also multiply everything by 2. Yeah, let's do that. So we have LM1G plus 2XM2G, all divided by D, 2D. Is that right? And we can factor out a G so that we don't have to type as many things into the calculator. LM1 plus 2XM2 all over 2D. Does that look good to you?
Yeah.
Okay, so that's the tension in the string A. Next, we want to get the tension in string B. So TB equals what?
So TB, I guess we should go to use point A for that one.
We could do that, but do you want to do torques again, or do you just want to do sum of the vertical forces equals 0?
Yeah, that would work.
We couldn't do that for getting TA because we didn't know TB. So we had to eliminate TB somehow. And we do that by summing up torques, because torques can be 0 even when the force is not 0. But when a force is non-zero, then you can't really eliminate any force because there's nothing that's non-zero. So we're going to do the sum of the forces in the vertical direction. Let's call it the y direction. We'll label this as y, and it would be a bit weird to label it as x when we have, because one of our lengths was given to us as x. So I'll just say f in the vertical direction. So what's the sum of all forces in the vertical direction? We have you agree with this?
Yeah.
Okay. So now we're just isolating for TB. So TB equals TA, which was that GLM1 plus 2XM2 over 2D. So TB equals TA minus M1 plus M2 times G. Okay, so we can simplify this a little bit. So how are we going to simplify this? We have 2dm1. We can't really simplify it very much. We can factor out a g. So we have g over 2d multiplied by lm1 plus 2xm2 minus 2dm1 minus 2dm2. That's what I'm getting at the end. Yeah, I mean, there's many ways we could write this final expression, but this one happens to be one that works, I think. And then it asks us now, what is going to be bigger, TA or TB? Which one is bigger?
Well, let me see here. Well, TA would be, yeah, TA would be larger because you could see that TB is just TA and minus both of the masses.
Yeah. So in order for this bar to not rotate around the pivot point B, which is a requirement for it to be in equilibrium, then we basically had that TA was this thing over there, and TB happened to be this thing minus M1G minus M2G. So it just happens that TA has to be bigger than TB in order for a system with this geometry to be in equilibrium.
All right.
So now the next question, it is to calculate X critical. So let me just see if I can pull up the question. Not there. Oh, where is it? Very strange. Very strange. I don't have the question here. It's weird. It just takes a long time to load. Oh, here. Okay, great. So part D. If the mass of the block is too large and the block is too close to the left end of the bar near string B, then the horizontal bar may become unstable. So the bar may no longer remain horizontal. What is the smallest possible value of x such that the bar remains stable? We're going to call that value of x critical. Express your answer for x critical in terms of m1, m2, d, and l. Okay, hint number 1. When the bar becomes unstable, there are only 2 points about which the bar can rotate. The points where the strings attach to the bar. About which point will the bar rotate when x is less than x critical? So if x is less than x critical, where do you think the bar is going to rotate? Around
Wait, sorry, could you say that again?
which part again?
Exactly, so the x critical is what exactly?
That is the x value at which, it's the smallest x value at which the bar becomes unstable.
And that's dependent on where the block is?
It's dependent on a lot of variables, but first the question is whether or not it would be whether or not the bar would rotate around string A or string B.
Right. Okay.
So I'm going to paste this question here. In case if you don't have this so if the mass of the block, that's M2, is too large and the block is too close to the left. So let's say M2, which is a distance x away from B. Let's say M2 is too far to the left. Like if you bring M2 closer and closer and closer together, closer and closer to point B or point A, eventually the bar is going to rotate, right?
Yeah.
And is it going to rotate around point A or point B?
Okay, so if the okay. I would think your string B. What's the smallest? I would say it would rotate around A.
That's correct. Yeah, that's correct. Yeah, it would rotate around point A. So that's the first hint. Now, the next thing, the next hint is, what is the tension in string B at the critical point? So when you move M2 to the left, you're moving M2 to the left. When M2 gets to the critical point X critical, what is the tension in string B?
The tension streaming. Okay. What's this? Okay, so that. So you're asking for just the tension in string B, or
Yeah. What is the tension in TB when M2 is at the critical distance?
well, the tension. Uh, the, thinking about. Okay, so I guess when it passes the critical point,
Yeah.
then I don't really know like how to answer it exactly.
Okay. Just 1 second. What's going on? I can't. What's this arrow doing here? When did I? Oh. What the line is doing there? This is weird. Delete that line. Okay. So why is it going to rotate around point A?
It's gonna rotate around point A. It's gonna do that because it's gonna. I'm sorry, I'm a bit confused. I don't. It's hard. Well, it's. Well, if it's too close, then it would be if it's. I, I I'm a bit confused.
Okay. What are you confused about?
Exactly what to say. I don't. can't think of an answer.
Okay, so we have block M2. It's moving to the left. It's moving to the left. It's moving to the left. What's happening to the tensions in TA and TB? What's happening as it's moving to the left?
It's increasing, right, to try to keep it in equilibrium.
Okay, let's look at the tensions. Okay, so tension. So TB is going to increase as X increases and it decreases as X goes down, right? So as I move M2 to the left, X decreases, and that means TB decreases, right? Because what's TB's dependence on X?
TV's depends on X. Well, if you look at the equation we made,
Yeah.
it's so it's G times 2X over 2D. So yeah, it's directly proportional.
Okay, so as I move M2 to the left, the tension goes down or up?
Well, the smaller X is, the smaller TB is.
Yes, so it goes down, right?
Yeah.
All right, and that happens with both TB and TA. But TA started off bigger, and TA started off bigger, and TA and TB both decreased by the same amount. So they both have a dependence of 2gxm2 over 2d. Here it's 2gxm2 over 2d. TB and TA have the same dependence on x, but TA just started off bigger than TB. So TA is still going to exist even when TB becomes 0. So TB will become 0 first, right?
Yeah.
And when TB becomes 0, then there's no tension here. Imagine if there's no tension, then you just have 3 forces. And TA is going to be larger than the sum of M1G and M2G, right? Because you're moving, it was in equilibrium, and now you're moving M2 to the left. This is the reason why it's going to rotate around point A, because point B, the tension TB is going to become 0. Then you have no tension there anymore. And then these masses are going to push on the bar, which will cause a rotation like that, right? If TB wasn't there, then you just have these two things pushing on the bar around TA, or around point A, right?
Yeah.
So that's the reason why it rotates around A instead of B. And what is going to be the tension at TB when we reach that critical point where it starts to rotate?
The tension, it would be so it would, did you see 0 or?
Yeah. Okay,
Yeah.
it's 0. Yeah. So basically we set TB to equal 0, and now we want to get X critical. We want to get X critical in terms of D, M1, M2, L. Yeah, just D, M1, M2, and L. So how are we going to do that? We want to get something. We know TB is equal to 0. How are we going to get X critical in terms of just L, D, M1, and M2?
We'll just D, M1, and M2. Okay, so I guess we could do TB is equal to 0 and then isolate for X.
Okay, so if you isolate for x when TB equals 0. Okay. To just get you on the right track, they actually gave a hint in this question. They said to calculate the sum of all torques around point A to get x critical. So we're going to do that. So we're going to do the sum of all torques around point A. That's equal to 0. And what are all my torques around? Now, TB is equal to 0. So what are all my torques around point A?
Well, so there is no tension in B, so it'd just be the both weights.
Okay. They're both negative.
Yeah.
And this is M2G times X critical. And yeah, so I have, yeah, that's exactly what it equals. And then this equals 0, right?
Yeah.
Hold on. We are doing this, the distance from M1, for the distance from the center of mass to point A is not equal to L over 2. That was a big mistake. It's not equal to L over 2 because we're doing the torque around point A. So what is the distance between the center of mass and point A?
Oh, you're talking about both weights, so that would be
okay. So the center of mass of the bar is going to be L over 2 minus D, right? It's L over 2 minus D. Yeah. And the distance between M2 and string A is going to be X critical minus D. So we just have to write those. So this is L over 2 minus D. L over 2 minus D. And then we have a negative torque from M2G, and that is a distance of X critical minus D. So that's 0 equals everything I have here. And I want to find X critical. So I have negative M1GL over 2 plus M1GD plus M2GD minus M2GX critical. And now I can isolate for XC. So X critical equals M2GD minus M1GL plus M1GD plus M2GD. This one, so this one, this one, this one. M1GL was divided by 2. So I'm going to multiply all of these ones and I'll divide by 2 times M2 times G. Do you agree with this for X critical?
Multiplied everything by 2.
Oh, no, I should have
Yeah.
had 2 here.
Yeah, that
And
I was about to bring that up.
yeah, good point. Very good point. So this one doesn't have the 2, right? Do you agree with this one now?
Yeah.
So yeah, I have M1GL. But that should be on the other side. No, okay, so I've moved X critical all the way over there. So then I have negative M1GL plus 2M1GD plus 2M2GD, all divided by M2G times 2. That looks to be correct as far as I can see.
Okay. So I guess we are done. Is that everything?
Yeah, that was that was what was asked for here. What was X critical, which is the distance at which M2, when you're moving M2 to the left, at what point does the bar start to rotate? And it rotates when the tension at B becomes 0. I guess if the tension at A became 0 first, then it would rotate around B. But because TA just happened to be bigger than TB, and TA and TB had the same dependence on X, which is the position of M2, then TB just became 0 first. So when tension at point B became 0, then the bar just rotated around point A. And then we wanted to find at what value of X critical did that happen. It happens when TB equals 0 and the sum of the torques at around A is 0. Does that make sense?
Yeah.
Okay, I'll give one more formula for X critical. It's possible to rearrange this in order to get D minus M1 over M2 times L over 2 minus D. That can be obtained, I suppose you would get, let me see what's happened here. We have M minus M1G L over 2 minus D. Yeah, and then we have, yes, that's right. Yeah. So you could just put this on that side, divide both sides. So you could put this part on the left side of the 0, M2G X critical minus D. That could be on the left side of the 0. And then you divide both sides by M2. So you'll get the negatives. The negatives are gone because you just have this. No, you have positive. So the negative will be gone because you do D minus L over 2 instead of L over 2 minus D. Yeah, we can do this. Let's just get this. Let's just obtain this. This is going to be, so by putting this on the left side, we'll get M2G X critical minus D equals negative M1G L over 2 minus D. Now let's divide both sides by M2. So then, in fact, we can divide both sides by M2G. We don't need, G is on both sides, so that's gone. And then this is an easy way to simplify this. So then we divide both sides by M2. we get x critical minus d. We can even put the d on the other side since we've gotten rid of this m2. So we have d minus m1 over m2 L over 2 minus d. Does that make sense?
Yeah, yeah.
So that's how we got this. That's how we got that. And I think this is correct, but it's not, it doesn't look that nice. So you can just ignore.
All right.
Got it?
Yep.
Okay. Okay, so we did 3 questions. Oh, how do I get rid of this? Okay, I think the computer's frozen. Oh, okay, it's good. All right, excellent. So I can post these slides in GitHub if you want.
All right.
Okay, then I'll see you tomorrow.
Yep.
Okay,
All right. See you.
see you.
Goodbye.
Bye.